So one of the applications we have is finding if you the algebra so you can go from one symmetry to another. Okay. More toward this condition. So I'm going to be showing a little bit about the library we have with us. Well, as a preliminary step, we needed the multiplication tables. So to get those, we used a Python program given by Hildebrand. Nice paper here. In that paper, it was supposed they said the program should work up to order 8. But we were only able to make it work up to order 6. But we wanted to order of 7. From the multiplication table, but was using 35. Make it be what to say. It's going from 5 to 6. Example, for any equals to, those are all the multiplication tables for the program, etc. Also, to use some library, we package Java, the linear algebra calculator. Download it, a very nice package. So, we have a big page, and to use files. First, data will contain files that have the multiplication and the actual library. It also gives some examples. These are programs we use for some articles. And, but there are some other examples of the full implementation of this library is available at and well, let's say, and we have examples of this. Some a brief description of the library. It contains some classes. First, it has a semigroup class that, well, that's the one that allows the calculation. Identify here the elements with numbers 1 through n. That's how it works. Then we had to build a particular set. We don't use Java default because it's for purposes. So we have to build a new one. And then we have a selector, and then we have a structure cancel. Then we have some child classes for them to have functionality for the different entities. Now I'm going to be talking about the algorithm defined to algebras are related. So the first thing we do to find out is two of the algebras are related and take the original algebra we want and perform a generalized expansion with to an unknown and group with an unknown number. And then we related the dimensions of the two algebras we want to connect. And impose conditions if we want, like a particular resonance entity. And then we extract information from the bracket of the standard extension, a new structure cancel, and this information about how the new of the but it doesn't give you completely. Not going to because of this part. So filling the blank is not have to fill it in a way that the table can see. Well, and so we have number of possible ways to feel anything. In this reference, some colleagues ask if particular real limit stated by an expansion by some set group, which one? They can be active. And they found that it was possible for type 1, type 2, type 1. But when they did that, they at some point had this table. So they were able to fill all these spots in the from the specific or from the general expansion. They had to fill all the other spots by hand. A long while to do it. In our library, we have one method in particular that's called field template. We get this template with blanks. It's going to fill it, and it's going to fill it as a semi-group. Do this, and we get this. There is two. We have this one, but we also have a method to see if semi-groups are the same by conformation. So they have an isomorphism, and we have marks to fill this, and our library takes it. So this is the result they get. For the type 1, you can relate them by many semi-groups. For type 2, you can relate them by those two in particular. For the type 3, they were able to relate them with this semi-group. And for type 4, just with this. Here we can see that the same semi-group is algebra and restricted to that any have more than one reduce, more than one resonance deposition. The resonance deposition you're using, you're going to get different. Another thing that has been done, and there is work to do here too, the preservation of some properties of the Lie algebra. The algebras also have some different classifications with it. We have a general Lie algebra, but they can be decomposed in a simple algebra, that's a solvable algebra, a simple, and so on. If you perform an expansion of a general Lie algebra, you get one Lie algebra. And if by a solvable, you get one helpful, you get one helpful. But in the other cases, you can get out of this one. Get a semi-simple and return to a semi-simple, or you can get out and get a general level. So it's also interesting to study. And in this article, they study how many extensions that give back to fully add. And for all the possible expansions with semi-groups order 3, they found it. And the expanded algebra, you have all these ones. And the gray ones preserve this simplicity. The resonance algebra, this one's only the 112, certain simplicity, and so on. Algebra is 2, and with a reduced resonance algebra, you get 12. So simplicity. For more semi-groups or higher orders, with harder, we can use the graphic. But we have similar results in this case. For example, for the order 6, we have general expansion and 201 of them result in simplicity. Algebra have 145 out of the 1,000. But we have over 25,000 resonances, but only 23 of them. And when you do the intersection, only. final remarks. As mentioned in the article, the full classification of the algebra is known only for the semi-simple range. The others are not known. There were many works using construction methods to see if they may help to find the classification of solvable Lie algebra. The answer was negative and remains a big problem in mathematics. And it was mentioned that it would be interesting to know whether that expansion might help better to see that. Therefore, apart from new physical applications, the program proposed in this course could be used for solving mathematical problems. It was really interesting to extend this library to other kinds of resonances. So now we only use the one as the joint, but there are others. For example, this one. This time of the composition would be very useful to study the expansion of the superalgebra using the concept of gravity theory, such as following. Apart from dimension application in gravitational theory and nuclear theory, it is interesting to analyze the two to look at the regulated. No, the manifold solution.
Particularly why you implemented Java. I probably only talk about Java in the conference.
No, well, I was familiar with the language. It was very comfortable to do so much numerical power, sort of symbolic. Thank you.